Okay, so this time we have two characteristic polynomials that look very similar. Same zeros, they both have two poles at the origin, but they also have a third pole. That's where they're different. So we're going to try to plot the root locus for both of these because something weird happens. And hopefully I know how to do it, but honestly, no guarantees. So we'll start with the one on the left, in which case this is our L, it's our transfer function, and our numerator is b of s, and our denominator is a of s. So first, we want to find the zeros in the pole. So our first zero and our only zero is -1, and we'll find our poles. So poles 1 and 2 are the same, they're 0, and pole 3 is -4. So the pole at 0 has a multiplicity of 2. And our first step is to count how many zeros and poles we have. So we have 3 poles, and we have 1 0. This is the number of poles, and this is the number of zeros. So since there are more poles than zeros, which is what we're always going to have because we want proper transfer functions most of the time, there are going to be 3 branches in this root locus. And then n minus n is 3 minus 1, which is 2. So there are going to be 2 branches with asymptotic behavior. Because you have to end at a 0, but there's not enough zeros for all the branches to end, so they can go off to infinity. Next, we are going to sketch out where our zeros and poles are. So we have 2 poles here, I'll label them 1 and 2. We have 1 0 at -1. That 1, so there's only one of them, and then we have a last pole at 1, 2, 3, 4. This is our third pole. Next, we're going to use the rule that any line segment on the real axis, which would be these 4 sections here, if there's an odd number of poles and zeros to the right of these lines, they're going to be included on the root locus. So here we have 1, we immediately see the second one, so you have 2, and so this is not included, this is not included, but then we get to our third one, and there is 1, 2, 3 of these points to the right of this line, so this will be included in our root locus. I'm going to draw arrows like this, really close to the pole and really close to the 0, because that's the behavior near them. They're definitely going to end there, but there might be some weird stuff happening. And then the last one, there are 4 zeros and poles to the right, so it's not included. Next, we need to calculate our asymptotes. So the formula for that is going to be given by find the point where the asymptotes are going to start at. Denoted by alpha. So this is the sum of your poles plus your zeros, all divided by n minus m. So first we add our poles together. Let's see. That's negative 4 plus 0 minus our zeros, which is negative 1 plus 1 over 2 over 2 which is going to be equal to negative 3 over 2, which is negative 1.5. So our asymptotes are going to be branching out at around 1.5. 1.5 down there. And we want the angles that our asymptotes are splitting off at. They're going to be equally separated, but we just need to find the first few poles. So that's denoted by phi L. 180 plus 360 times L minus 1. L is basically the number corresponding for like first asymptote, second asymptote is like L equals 1, L equals 2. And this is going to give us 2 angles. So that would be 180 degrees over 2, which is 90, for L equals 1. And then it'll give us 360 plus 180, 540 over 2, which is equal to 270, or equivalently negative 90, or L equals 2. So there's only 2 of them because I only need 2 asymptotes, and that's going to be 1 asymptote going up for 90, 1 asymptote going down for negative 90. So that means we're going to be expecting our two branches that go off to infinity to be following those lines. And now we want to calculate our breakaway angles. So we're going to have a breakaway here, and I don't know if we're going to have another one. This one I don't believe results in another breakaway, but there's definitely going to be one here, because usually when you have 2 poles right next to each other on the real axis, they're going to be exiting both poles, sometimes towards each other, and when they're going towards each other, they're going to collide and break away. And so this is a breakaway point, except these poles are getting closer and closer together, and eventually they just become one point, but they're still getting breakaway point. They're still breaking away vertically away from the real axis. So that's going to happen, but I'm going to try to calculate it using the rule of first we solve for k. So we start from this equation here. I'll just take it with me. And we're going to solve for k. So k is equal to, let me skip a few steps here. Except when I skip steps, I can't do math. And k is equal to 3 minus 4 s squared for s plus 1. And we're going to take the derivative of this with respect to s. And we will get 3s squared minus 8s times s plus 1 to the negative 1 plus, I just always do quotient rules product rule because I can't remember which one comes first and which one gets a negative sign. Squared times, there will be a negative 1, s plus 1 to the negative 2. And if we write that back into fractions, we'll get some cancellations of negative signs. And then we want to set this equal to 0. And we can split off the denominator by multiplying it to both sides. And multiply out. And combining like terms. So this will give you negative 7, 8, 0. And then if you solve for these, well, you have, actually do a bit more factoring. 8, 0. You'll get s equal to 0 or s is equal to negative 7 plus or minus radical 49 minus 4 times 2 times 8 over 4. If we evaluate the inside, we get 9 minus 4 times 2 times 8. We get negative 15 under a square root, and that means that this s does not exist. For breakaway points, we don't care if they're complex because we're on the real axis. So our only breakaway or break-in point is going to be at s equals 0. Scrolling back up to here, that's exactly where we said it would be. So we'll have one breakaway point, and then we'll go and follow the asymptotes. Are you talking to people or you just